Hello and welcome. Today we're going to take a deep dive into a fascinating review paper titled AI for Manufacturing and Healthcare, a Chemistry and Engineering Perspective. This work explores how artificial intelligence, or AI, is not just improving existing processes in these fields, but enabling entirely new capabilities. The authors begin by establishing that AI and machine learning approaches are revolutionizing science, engineering, and industry. The opportunities are vast, ranging from designing and screening molecules automatically to predicting material properties to understanding the mechanics of chemical reactions. In the world of engineering, this translates to computer-aided design, predictive maintenance for complex systems, and the control of robotics and autonomous vehicles. This review focuses specifically on new applications in two critical sectors, manufacturing and healthcare. For manufacturing, we'll explore AI's role in batteries, flow chemistry, additive manufacturing, sensors, and machine vision. In healthcare, the focus will be on medical vision, diagnosis, protein design, and drug discovery. Finally, we'll touch on some crucial surrounding topics: how to integrate physics into machine learning, the importance of model explainability, and the security and governance required for deploying these powerful models.
At its core, navigating the immense space of chemistry and engineering can be viewed as a massive optimization problem. The authors highlight a staggering fact. The number of substances synthesized in all of human history is on the order of 10 to the power of 8. But the number of potential candidates, for example, the number of drug-like molecules, could be as high as 10 to the power of 60. This is a search space so vast it's impossible to explore through traditional trial and error experimentation. This is where machine learning offers a new path forward. The paper presents a powerful method for tackling this challenge using a class of algorithms called probabilistic generative models. The first step is to represent a molecule in a way a computer can understand. A common method is the Simplified Molecular Input Line Entry System, or SMILE string, which is essentially a text-based representation of a molecule structure.
The authors illustrate a framework based on an autoencoder. Think of an autoencoder as having two parts, an encoder and a decoder. The encoder network takes a discrete SMILE string and compresses it into a continuous fixed-length vector. This vector is a point in a high-dimensional space called the latent space, which serves as a continuous representation of the molecule. The decoder network does the reverse. It takes a vector from this latent space and attempts to reconstruct the original SMILE string. A key challenge is that not every point in the latent space corresponds to a valid, chemically possible molecule. To address this, the framework uses a specific type of autoencoder called a variational autoencoder, or VAE, which helps ensure that the generated molecules are valid. Once a molecule is represented in this continuous latent space, we can start to optimize it. An additional network, a multi-layer perceptron, or MLP, is trained to predict a molecule's properties directly from its latent space vector. With this predictive model in hand, we can use gradient-based optimization, a mathematical technique for finding the maximum or minimum of a function, to search the latent space for new vectors that correspond to molecules with desirable properties. These new vectors are then fed to the decoder, which generates new SMILE strings for molecules that, in theory, should have the properties we're looking for. These candidates can then be synthesized and tested in the real world. The paper provides a beautiful illustration of this process. An optimization was performed with the objective of finding molecules that are both easy to synthesize and drug-like. The objective function was a combination of the synthetic accessibility score, or SAS, and the qualitative estimate of drug-likeness, or QED. We can see a violin plot comparing the results of this VAE-based optimization against other methods like random searching and a genetic algorithm. The VAE approach consistently finds molecules with higher objective scores. A principal component analysis plot shows the starting and ending points of these optimization runs within the latent space. Most impressively, we can see the actual path of optimization. The process starts with a specific molecule, and by taking small steps through the latent space, the algorithm gradually transforms it. Along the path, the decoder generates the intermediate molecular structures, showing a step-by-step evolution towards a final molecule that has a much higher percentile score for the desired properties.
This example provides a specific look at the process, but the authors then zoom out to present a more general workflow for supervised learning. It begins with a known labeled dataset. This data is used to optimize a model, which involves steps like feature generation, data splitting into training and validation sets, and hyperparameter optimization. Once the model is converged and performs well, it can be used to estimate the properties of an unknown, unlabeled dataset. This process is at the heart of what's called virtual screening. Instead of synthesizing and testing millions of compounds, we can start with a large candidate space, perhaps generated combinatorially. Virtual screening, using the trained AI model, eliminates most of these candidates, leaving a much smaller, more manageable hit space of promising molecules that can then be subjected to more expensive and time-consuming experimental tests. To understand where these AI techniques are having the biggest impact, the authors analyzed trends in journal articles and patents from the Chemical Abstract Service from 2000 to 2020. The data reveals that small molecules are by far the most dominant substance category in AI-related journal publications. This is likely due to their relatively simple structures, which are easier to represent and model. In the world of patents, however, nucleic acid sequences and peptide sequences dominate, reflecting significant commercial interest in biologics and genetic technologies. The trends show a clear and distinct increase in AI adoption across the board, particularly in the last decade. This analysis justifies the paper's focus on soft materials and ionics, as they represent the majority of AI publications and are driving much of the development. Of course, any AI research depends on the quality and availability of data. While it's possible to build a dataset from scratch, the authors point to several important, curated, open datasets that are crucial for training these algorithms. These range from ANI1, which contains quantum mechanical calculations for millions of organic molecule conformations, to Zinc, a massive database of commercially available compounds for virtual screening, to numerous specialized datasets for material science, chemical reactions, and battery performance. The algorithms used in this research generally fall into one of three major categories. The first is supervised learning, which uses label data where the ground truth answer is already known, to train a model to make predictions. This category includes everything from linear regression to powerful deep learning models like convolutional neural networks, or CNNs, and recurrent neural networks, or RNNs. The second category is unsupervised learning, which works with unlabeled data to discover hidden patterns or structures. K-means clustering, which groups similar data points together, and generative models like autoencoders and generative adversarial networks, or GANs, fall into this category. The third and distinctly different category is reinforcement learning. Here, an agent, like a chess playing program, learns by interacting with an environment and receiving rewards or penalties for its actions. Its goal is not to minimize an error function, but to maximize its cumulative reward over time. There also exists a middle ground called semi-supervised learning, which uses a combination of a small amount of labeled data and a large amount of unlabeled data for training. Graph neural networks, or GNNs, which operate on graph-structured data, have shown great promise in this area. Beyond the models themselves, a new set of tools is emerging to help researchers extract knowledge from the vast body of scientific literature. Natural language processing, or NLP, is key here. A powerful model called BERT, which stands for Bidirectional Encoder Representations from Transformers, has been particularly influential. BERT is pre-trained on a massive amount of text, allowing it to understand language context in a sophisticated way. Researchers have created specialized versions like SciBERT, trained on scientific papers, and BioBERT, trained on biomedical text, to perform tasks like automated data extraction. This has even led to tools like Battery Data Extractor, which can automatically pull key data and classifications from battery research papers. And of course, large language models and chatbots are now becoming common tools for interacting with this information. Now, let's turn our attention to the first major application area, manufacturing. AI is fundamentally changing how we design, make, and inspect industrial products. For example, it's being used for generative design, tool life modeling, and robotic control. The paper presents a comprehensive diagram of how different machine learning concepts connect to manufacturing applications. At the top level, we have the learning paradigms we just discussed: supervised, unsupervised, and reinforcement learning. These paradigms inform the choice of specific techniques or models, such as decision trees, neural networks, or clustering algorithms. These models are then applied to learning tasks like regression, classification, or anomaly detection. Finally, these tasks enable downstream industry applications, including predictive maintenance, quality control, process optimization, and industrial automation. To make this concrete, the author showcases a self-driving laboratory named Ada. This automated platform is designed for chemical and materials research, specifically to self-optimize experimental design and execution. Ada consists of 2 robots with overlapping workspaces. One robot, a 4-axis arm, is responsible for synthesizing thin film samples by mixing precursors, casting them onto a substrate, and annealing them. The second, larger 6-axis robot transfers these samples for characterization, including imaging and conductance measurements using a 4-point probe. After a sample is made and characterized, a machine learning algorithm predicts and decides the synthesis parameters for the very next sample. The goal is to maximize the thin film's conductivity. The results are displayed on a plot of the Pareto front, which represents the optimal trade-off between 2 competing objectives, in this case, combustion temperature and conductivity. The AI systematically explores the parameter space to find the synthesis conditions that lie on this optimal front, demonstrating a closed-loop system where the AI learns from each experiment to guide the next.
With this foundation, let's dive into the specific areas of manufacturing, beginning with batteries. The demand for better energy storage is immense, and while lithium-ion batteries are effective, there's still significant room for improvement in their lifespan, performance, cost, and safety. The discussion here is broken into 2 subtopics. First, battery management systems, or BMS, and battery life models. A key concern is battery failure, which can pose serious safety risks. A BMS is the electronic system designed to monitor and control a battery's operation to ensure optimal performance and safety. It tracks critical parameters like state of health, or SOH, which reflects the battery's current capacity compared to its initial state, and state of charge, or SOC, which is the current energy level. Predicting SOH and SOC is a perfect task for AI. The paper outlines a typical machine learning pipeline for SOH estimation. It starts with data acquisition, collecting data on voltage, current, and temperature during battery tests. The next step is data processing, which involves feature engineering, extracting meaningful signals from the raw data. This can include techniques like incremental capacity analysis or differential voltage analysis. These features are then used to train a model, which could be anything from a support vector machine to a long short-term memory, or LSTM, network. Finally, the model's output, the SOH estimation, is evaluated using metrics like root mean squared error. SOH can be measured directly in a lab, but these methods are demanding. Data-driven methods, on the other hand, can establish a correlation between SOH and real-time battery signals, making them much more practical for real-world applications. Unlike SOH, there is no direct way to measure SOC. The estimation pipeline is similar, but the methods are different. They range from simple lookup tables to more sophisticated filter-based methods like the Kalman filter, to purely data-driven methods like artificial neural networks and deep learning. While data-driven methods require little prior knowledge of the battery system, their performance is highly dependent on the quality of the training data. Another critical metric is the remaining useful lifetime, or RUL, of a battery. This is a complex, non-linear prediction that depends on the battery's entire usage history. The paper outlines 3 approaches for RUL prognosis: deterministic machine learning, filter-based methods, and stochastic methods. While deep learning can offer high accuracy and fast response, the complexity of the models can lead to issues with overfitting and explainability. There is often a trade-off between the accuracy of a model and its complexity. The second subtopic is battery design. Here, machine learning is accelerating the discovery of new and better battery components. Models are being used to screen thousands of candidate materials for cathodes, anodes, and electrolytes to identify those with the most promising properties, such as high energy density and durability. The authors describe a closed-loop framework that combines a physical system, a digital twin model of that system, and an AI engine to drive the design, discovery, and management of new battery technologies. Next, we move to chemistry and automation. AI is being used across all 12 major categories of chemistry, from pharmacology to material science to organic chemistry. An analysis of interdisciplinary publications shows that AI is creating new connections between fields. For example, there are strong AI-driven links between analytical chemistry and biochemistry,
and between material science and physical chemistry.
Network analysis of research concepts reveals interesting trends. Early on, around the year 2000, AI in chemistry was often associated with neural networks being used for quantitative structure-activity relationships, or QSAR. More recently, topics like diagnosis have emerged, linked with a whole suite of modern algorithms, like deep learning, random forests, and support vector machines.
A key area of automation is flow chemistry. Unlike traditional batch processing where reactants are mixed in a flask, flow chemistry involves pumping reactants through an optimized reactor in a continuous stream. This allows for better control, improved efficiency, and enhanced safety. While the initial investment is higher, the process improvements can be substantial. AI is perfectly suited for optimizing these flow reactors. For single objective optimization, algorithms like SNOBIF can be used. For more complex multi-objective problems, Bayesian optimization, or BO, is an excellent choice due to its ability to work with sparse data. The paper presents a case study of a self-optimizing flow reactor for an aldol condensation reaction. The system uses a multi-objective optimization algorithm called TSEMO to simultaneously optimize for multiple competing goals: yield, cost, and a metric called the E-factor, which measures waste. The algorithm controls the reaction parameters, like molar ratios and temperature, and uses online HPLC measurements as feedback to intelligently explore the parameter space and find the optimal Pareto front of solutions. Reinforcement learning is also being applied here for multi-step processes, and neural networks are being used in closed-loop systems to discover entirely new organic compounds by interpreting real-time NMR and mass spectra data and deciding on the next reaction to run. The third area in manufacturing is additive manufacturing, or AM, also known as 3D printing. This process builds objects layer by layer, offering incredible flexibility for complex geometries and mass customization. Machine learning can be effectively combined with the automation inherent in AM. The paper describes a system called BEAR, which is used to study the mechanics of additively manufactured components. It consists of 3D printers, a robotic arm, and a universal testing machine. The system can print a family of parametric structures, like a crossed barrel, and then mechanically test them to failure. The resulting force displacement curves reveal different behaviors. Some designs are too strong, some are brittle, and some are ductile, exhibiting desirable strength after an initial yield point. The challenge is to find the design parameters that produce this optimal ductile behavior. This is another optimization problem, and the authors show how Bayesian optimization can be used to solve it with remarkable efficiency. They compare two decision-making policies: maximum variance, which prioritizes exploring unknown regions of the design space, and expected improvement, which focuses on exploiting promising regions. The simulations show that the expected improvement policy is far more efficient, achieving a 60-fold reduction in the number of experiments needed to find high-toughness structures compared to a more random sampling approach. The fourth area is sensors. The growth here is explosive, driven by sensor fusion and the Internet of Things, or IoT. When combined with machine learning, sensors allow systems to monitor, understand, and respond intelligently to their environment. A major focus is sensor fusion for autonomous vehicles. AI-powered techniques are needed to combine data from a suite of sensors, like cameras, LiDAR, and radar, to build a comprehensive, real-time understanding of the vehicle surroundings. Several traditional algorithms are used for this. Common filters and their nonlinear extension, extended common filters, are recursive algorithms that estimate the state of a system. Particle filters use a set of weighted particles to represent the probability distribution of the state, making them more robust in complex environments. Dempster-Shafer theory provides a mathematical framework for handling uncertain and conflicting information from different sensors. In addition to autonomous vehicles, AI-driven sensors are crucial for industrial automation, where Bayesian networks can model complex dependencies, and for the vast distributed networks of IoT devices. This brings us to a particularly compelling example in healthcare and wearable sensors: continuous glucose monitoring for diabetes patients. The paper showcases a technique called data assimilation, or DA, which synchronizes a mechanistic model of human glucose metabolism with sparse, real-world data from finger prick measurements. We see the training data, a few finger prick glucose measurements and meal carbohydrate information over 2 days. The data assimilation model then produces a continuous forecast of glucose levels. When this forecast is compared to the actual data from a continuous glucose monitor, which was hidden from the model, the overlap is striking. Despite having very little input data, the model was able to accurately track the glucose dynamics.
A comparison highlights the power of this approach. A standard spline smoother, which is unconstrained by physiology, can deviate wildly from the real measurements. The data assimilation model, however, leverages hard-coded physiologic knowledge. This decreases the model's flexibility but dramatically increases its accuracy, allowing it to infer dynamics that would be impossible to capture from the sparse data alone. This approach has broad implications for pharmacodynamics, sleep monitoring, and many other areas of medicine. The final area within manufacturing is machine vision. Deep learning has revolutionized the ability of computers to interpret data from images. In manufacturing, machine vision assists with robotic guidance, component inspection, and optical metrology. The paper provides an excellent example from material science, analyzing a transmission electron microscope, or TEM, image of a polyvinylidene fluoride block polystyrene polycopolymer. The image shows crystalline domains as darker regions and amorphous domains as lighter ones. A machine learning model, trained by a user on predefined regions, is then used to automatically classify every pixel in the image, creating a semantic segmentation map of the crystalline, amorphous, and interface regions. The output is not just a classification, but a probability map, indicating the model's confidence for each pixel. This example opens the door to a deeper discussion of machine learning for microscopy. Different microscopy techniques generate a wide variety of image data, from the atomic to the mesoscale. The paper outlines the common deep learning models used for these tasks. For segmentation, UNet architectures are popular. For classification, ResNet is often used. For image reconstruction or enhancement, generative adversarial networks, or GANs, are powerful. And for tracking objects over time in videos, recurrent neural networks like LSTMs are employed. To make these advanced techniques more accessible, a number of pre-trained models and open-source platforms have been developed, such as Micronet, a large dataset of labeled microscopy images, and the Bioimage Model Zoo. Applications of these models are transforming microscopy. For image enhancement, a deep learning model called CARE can be trained on pairs of low-quality and high-quality images. It learns to denoise and restore the low signal-to-noise images, producing results that look remarkably like the high-quality targets. This can enable imaging with significantly lower and less damaging illumination doses.
For image segmentation, we saw the polymer example. This can be applied to biological images as well. For instance, to segment mitochondria or neuronal structures from electron microscopy volumes.
More advanced models can classify complex structures, such as different types of carbon nanotubes, using features extracted from deep within a convolutional neural network. Another key application is object tracking. Modern microscopes can capture high-quality videos of dynamic processes. Deep learning models, often based on a UNet architecture, can be used to track single cells as they move and divide, or even to track the 3D motion of individual nanoparticles from their holographic scattering patterns. In conclusion, this review paper provides a comprehensive and insightful look into the current state of AI in manufacturing and healthcare from a chemistry and engineering perspective. From designing new molecules in a virtual latent space to guiding self-driving labs, optimizing 3D printing, and interpreting complex microscopy images, AI is not just an incremental improvement. It is a foundational technology that is enabling new ways of conducting research, discovering materials, and developing products.